Okay, so this is a little addition to our motor load calculations class that we just had. We're going to work a few sample problems. It's actually one sample problem all kind of put in together. We're going to take 4 different motors, and we're going to calculate that all the way back to the feeder breaker. So if we look at our problem to start with, we have a feeder that supplies the following motors from a 240 volt source. All the motors are continuous duty. All the breakers are going to be inverse time delay. We have a 15 horsepower induction motor with a service factor of 1.15 and a full load amp of 36 amps on our nameplate. We've got a 25 horsepower induction motor, 44 degrees Celsius rated, 62 full load amp motor, a 10 horsepower induction motor, temp 38 degrees Celsius, full load amps of 25 amps, and then a second one of that exact same motor. So we're gonna work our way through that worksheet. If you've got that worksheet that's in Blackboard that we handed out in class, that's going to help you a lot here because we're going to work each of these steps one by one as we go through the list here, right? Step 1 is going to be to find the full load current for each of these motors. Remember, full load current, that's our code book current. That's what is listed for the horsepower of each of these motors in table 430. They're all 3-phase, so 430.250. Right? So where you look at our full load current for each of these motors, all will be found in 430.250, 3-phase AC full load current for motors table. We're going to look right, so we have 240 volts. Everybody's going to be in this column right here. It says 230 volts, but the voltages listed are rated motor voltages. The currents listed shall be per system voltage ranges of 110 to 220 and 220 to 240. So our 230 volts does fine for our voltage there. Our 15 horsepower is going to be 42 amps. Our 25 horsepower is going to be 68 amps. All right, so our 25 horsepower, 68 amps. Our 10 horsepower, 28 amps. And then our second 10 horsepower, also going to be 28 amps. All right, so now we have our full load current for each of our motors. Next, we got to find what wire size we need. Well, if we just found our full load current, then we've got our FLC for each of those motors. We have 42 amps, 68 amps, 28 amps, and 28 amps. They're all continuous duty, so we're going to multiply each of these by 125%. And so we're going to get 52.5, 85, 35, and 35, right? Pause this video, work out the math for yourself before we get this, so that you know that you can do it, right? Pause the video as you get to these spots, work the math. 42 times 1.25 or 125%, 52.5 amps. 68 times 1.25 gives us 85 amps. And then 28 times 1.25 gives us 35 amps. Well, now we're going to look at our chart here, right? So if we've got 52.5 amps for the 15 horse, it's going to need a 6 AUG, right? Can we see that? Because we're going to get, it's less than 100 amps. If it's less than 100 amps, we have to use this column, right? Because we don't know what the terminals for all the other devices that are hooked up into this circuit, we don't know what they're rated for. So if it's less than 100 amps, we use the 60-degree column, right? So that 52.5 amps, right? We round up to the next one, 55 amps gives us a 6 AUG. Next, that 85 amps, right? That one's going to be pretty easy. That one is 85 is 85. And then for the 10 horsepower, 35 amps, we're going to be using the number 8 for both of those there. Now, we can take our from the little sheet that I gave you, right? The little sheet that you've got, it has a diagram that we can put our numbers into, right? That diagram is just sort of meant to give you a place where you can put all the things that you need to know, right? So we've got our full load current in the little circles, right? That represent our motors. That's our full load current for each of our motors. And now we've got our wire size for our branch circuit, right? The wire that goes to each of our devices, that's our branch circuit. So next we need to find our thermal overload rating. And so to find that, right, we're going to look at step 3 on our sheet here, right? Step 3 is we're going to take our nameplate amps. This is the only place where we use our nameplate amps, our full load amperage from the nameplate. And we're going to find the number that falls between 430.32A and 430.32C, right? Those two little charts. And what those charts tell us is that if we have a service factor, let me get my pen out. If we have a service factor 1.15 or greater, we're going to do times 125%. Right, like we got right there, 36 amps times 125%. If we have a temp rating of 40 degrees Celsius or less, 125%. Everything else gets multiplied by 115%. And the reason that we got this percentage that's over the motor, right, is when we're running a motor, it has a rated amperage that it runs at, but it draws more amperage on startup, right? And so these overloads, they allow for that startup time. We need for it to be a little bit larger than the running amperage, because if it tripped at running amperage, it would always be tripping, and we want it to be a little bit higher so that once we put a load on that motor, if we overload it a little bit, if we overload it by 15 to 20%, we're going to trip that motor. So if we do that first one, right, 36 amps times the 125%, we get 45 amps. If we do the next one, we're going to get 71.3 amps. If we do the next one, 25 amps times 125%, 31.25 amps. And if we do this last one, same thing, 25 amps times 125%, we get 31.25 amps. So these are our minimums, right? This is the minimum that we can set those at. But this is where we need to try to set it here, and then if it fails at these settings, then we can go up to the setting that's 140% or 130% if it's an other, right? If it's an other, it'll be 130%. If it's one of these two, we're going to up it to 140%, right? But as long as it'll run at this lower one, that's where we're going to want to run it. And we'll put those into our little sheet, right? A little cheat sheet that I'm putting these numbers in as we go, so that as I work my way back, I have all the answers for all these different things, right? So when you take your exam, you'll want to be able to fill these things in, so that if I ask you what the full load current is for motor number 3, if these would be labeled 1, 2, 3, 4, if I asked you what the full load current for motor number 3 is, be able to tell me it's 28 amps. If I told you what size thermal overload you needed for motor number 1, you'd be able to tell me that it needs a 45 amp thermal overload, and those are the things that we're working towards here. Now we're going to move on to step 4, our branch circuit overloads. Now, I mentioned in our lesson, right? These can make you freak out just a little bit when you look at some of them, because we're going to be talking about, all of these have fairly decent size amperages for the motors, but we talk about having amperages for our breaker that is much larger than what the wire is designed to hold. But the wire, we're not sizing the breakers on the wire size here. We're sizing the breakers on the motor size. Our thermal overloads that we just talked about in step 3, that's what's protecting our wire at the threshold that is good for the size of wire. These breakers, these breakers that are for our branch circuit, these are designed to protect us from the short circuit. Right? Our other motors are protecting us from, a heat overload from just a little bit too much amperage. These breakers are protecting us from a some type of a short circuit. And if we have a short circuit, even if we're looking at this 800 times 800% column, a short circuit is almost infinite amperage. It's running towards infinite amperage until the wire comes apart, and so we're gonna obviously trip well before the wire comes apart, even at 800%. All right, so let's, if I can find there we go. So let's work through these. Right, we've got our 42 amps. These are all inverse time delays, right? We talked about using the inverse time delay breakers in both locations. And by using that inverse time delay, I can use a breaker that is only 250% the size instead of 800%. So our 42 amp load that we've got right here, if we look at this is our chart for 420.7, no, 240.7, I believe it's 240.7. This is the chart that tells us all the different the standard breaker sizes. So if we got a 42 amps times 250, you're going to get 105 amps. So there's not a 105 amp breaker, so we're going to size that up to a 110. Then we have a 68 amp full load current times the 250. We're going to get 170 amps. There's not 170, so we're going to size up to the 175. Then we're going to take our 28 times 250, and our 28 times 250 is going to be 70 amps, and there is a 70 amp, and so that does make it a little bit easier for us. And so that's our 3 different sizes that we've got. Then we're just going to plug those into our table, into our chart there, so we know what size branch circuit overloads, what branch circuit breakers, what size do we need. Step 5, feeder conductor size, 430.24. It's saying we're going to take 125% of our largest motor's full load current and then add all the other motors' full load current to this total. And then we're going to use our chart 31016 to select a wire size. All right, what's all that saying? So what it's basically saying is for our feeder circuit, our feeder conductor, that is our wire that's going to be connected that's feeding all of these circuits, right? It's going to feed all of these different circuits. And so if we need to feed all of those different circuits, it needs to be big enough to handle the amperage of all of those motors. But it doesn't, like, we're not expecting for all of those motors to be running over capacity at the same time. So we only pad the largest one, and then we can downgrade all the others. Not downgrade, but we won't have to pad them up for all the other motors. So we take our first motor, our largest motor, not our first motor, but our largest motor. It has a full load current of 68 amps, which we are going to multiply by 125%. And then we're going to add 42 amps, and then add 28 amps, and then add 28 amps, and we get 183 amps total, right? So if we have 183 amps total, we need a wire that can hold 183 amps. Now, because we're looking at over 100 amps, we get to look at the 75-degree column, right? Because if it's over 100 amps, then all of the devices are required to have terminals that are good for at least 75 amps. So we can use a 75 amp column if it's over 100 amps. All right, so 183 amps. I'm going to scroll down here till I got 175. I got 200 amps, and that is going to be a 3/0, a 3/0 AUG wire. And then we're going to, we've got that plugged into our little table. All that's left is our feeder breaker, the breaker that feeds the entire circuit, and that's what we'll do next. Next, we're going to do our feeder overcurrent size. This is step 6, and this one it's a little weird because what we're going to do is it's asking us for our this is for our feeder breaker, and it asks us to find the largest branch circuit breaker, which is going to be this one right here, 175 amps. We're going to take that largest branch circuit breaker size, the amperage size, and then I'm going to add the other amperages to it. I'm not the breakers, right? I'm not looking at the breaker size. I'm looking at the actual full load current of each of those other motors. And so I'm going to take my 175 amps and I'm going to add 42 amps to it. So I have the 170 amp breaker, and then I have 42 is my that looks ugly, my FLC, my full load current of the first motor. And then I want to add my 28 amps for my second motor and my 28 amps for my third motor. And I'm gonna add all 4 of those things together to get 273 amps. Now, everywhere we've worked on everything here so far, we have upped the amperage. We have upped it to the next size up if it didn't match exactly what we needed. This is the one place where we come down, right? Because we're not expecting for all of these devices to be getting turned on at once, right? Like that extra overcurrent space that we have given these devices, we give it that space for startup, that extra amperage that gets drawn at startup. We're not expecting for all these devices to hit that peak startup amperage all at the same time. So this is a spot where we're allowed to round down. Right here again is our table. This is our table 240.7, and so I find, we got a 300. Let me find we've got a 300, and then we have a 250. So we're going to come down to our 250, and we're going to install a 250 amp inverse time delay breaker there. All right, and finally, here is a little homework problem for you. You can bring this in with you when you come to class. Try to work it. We'll work this one in class once class starts. But if you guys show it to me before class starts, we'll put 10 bonus points. This will be your bonus for your exam. You don't have to have it complete, right? If you just show me that you've started it, right, we'll put 10 bonus points onto your exam that you're taking next week, just to show me that you guys are actually watching the video and actually taking part in the video and trying to do the online material as it comes along. If you will, just copy down your parameters here and see if you give it a shot. Work through step by step of the worksheet that's on Blackboard. See if you can fill this in all the way. If you can, that's awesome. If you can't, right, we're going to go over it in class on Monday or Tuesday next week, depending on when you have class with me, and we'll see if you guys can tell me where your stumbling blocks are, where the places that you're struggling, and we'll see what we can do there. Like I said, if you can't complete it, right, if you're struggling in a spot, just bring it with you to class on Monday. We will go over those things. But like I said, I'll have a moment where you can show me that you have at least started on it, and that'll be worth 10 bonus points on your exam.